Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're now going to introduce the concept of the dynamic allocation of arrays. So in this topic, we will discuss the allocation, accessing and manipulation, and deallocating of arrays. We will learn how to use initialization and understand the costs, and we will learn about what happens when allocations of larger arrays fail. All right, in the last topic, we allocated instances of a type. So here we requested sufficient memory for a variable of type int, and we initialized it with the value 91. So right now, somewhere in memory, there's 4 bytes allocated, and those 4 bytes contain the value 91. The local variable p_int stores the address of that location. Here we're going to print out that address, and then we're going to print out what is there. Now we're going to change what is there by assigning to what is at that location the value 7. We can now use the value that is there in any arithmetic statement, just like we could have before with a local variable of type int. So here, whatever is at that location, I add 1 to it, and I multiply that by whatever is at that location minus 1. So in this case, because the value stored there is 7, this will print out 6 times 8, or 42. Finally, now that we no longer require that memory anymore, we can tell the operating system, hey, whatever memory you allocated for me here at this address, I don't need it anymore. That's what the delete statement does. However, p_int still has the address. So we now technically have the address of something that we have explicitly told the operating system we don't need anymore. So it's just safer right now to set p_value or p_int to the 0 pointer or the null pointer. So in this case, if we were to execute this program, the output may appear something as follows. Again, the address at which the integer is allocated is probably going to change every single time you execute this program. So now, how do we allocate and deallocate arrays? Well, interestingly enough, it's more or less the same. The only difference is that we have to tell the operating system how large the array is. So here we have requested for the operating system an array for 100 integers. So the compiler will ensure that a request is made for 400 bytes. The empty braces indicates that all of the entries in this array will be initialized to the default value, which is 0, and then that address, the address of the first byte of the first entry of that array, will be returned and assigned to the local variable array, which is, again, a pointer. We can print out that address, and then we can use that array just like we can use any local array. So here I'm printing out the 19th entry, which is going to be 0 because, again, remember we initialized everything to 0. I will then assign to the 19th entry the value 2, and here I'm going to use that 19th entry in an arithmetic expression, 7 times 2 times 3, which is 42. So that will be printed. Here, once again, I'm going to deallocate the memory for the array. However, I must be very careful because I allocated an array and not just one int. I must call delete with the square brackets immediately following it. That indicates to the operating system and to the compiler that this was an array that had been allocated, and now we are deallocating that array. Once again, however, nothing happens to the local variable array. Array continues to store the value of that first address. So just to be sure, we set array to be 0, or the null pointer. All right, so if we run this, we get exactly what we would expect. We get the address of the array, wherever it was allocated. We get the initial value that's at array 19, which is 0. And then, having set the index 19 of the array to 2, we then print out 7 times 2 times 3, which is 42. Now, initializing all the entries of an array can be potentially very expensive, so you can opt out of this. So, for example, here, array is a local variable which is a pointer to a double. And now we are asking the operating system for an array of the given capacity of doubles. Well, the capacity is 100, and therefore this will make a request to the operating system for 800 bytes, as each double occupies 8 bytes. So the operating system will find 800 bytes, and it will return the address of the first byte of the first entry of that array. Now, if we print out, say, the 15th entry of the array, whatever is there is going to be interpreted as a double. So there's a whole bunch of random ones and zeros, and whatever they happen to be, that is what is going to be interpreted as a double. Now, here we have a for loop that is going to initialize all of the entries of the array. So the kth entry of the array will store the value of sine of k divided by 10. Notice that because k is indexing into an array, its type is given as standard size underscore t. Following this, we're going to print what is at index 15 of this array. We will then set the index 15 of this array to 1.0, and then we will use that entry in this arithmetic expression. Now, in this case, because we know that the 15th entry is now 1.0, we can deduce that this is going to print out the product 1.5 times 0.5, which is equal to 0.75. As before, we will now tell the operating system we no longer require this memory, and the operating system will deallocate or no longer flag those 800 bytes as being allocated to this particular program, and therefore, to be safe, we will set the local variable array to be equal to the null pointer. So, if we were to execute the program, here's what we see. The value at that entry of the array is something very small, but that's just interpreting whatever's there as a double. When we next print out what's at array 15, that is sine of 1.5. We set that to 1, and then we print out the calculation of 1 plus 0.5 times 1 minus 0.5. Now, once again, naming conventions are useful. Previously, a local variable would be given an appropriate, usually singular name, as it's storing an object of a specific type. And if it is a local variable or parameter that is a pointer, we may prefix that identifier with a p underscore. Arrays should be some sort of plural word indicating some sort of collection, or it may contain the word array or table within it. Alternatively, especially if you're dealing with dynamically allocated arrays, you could prefix the identifier with an a underscore to emphasize that it is a pointer, but is a pointer to an array. Now, suppose you make a request to the operating system for an absolutely huge amount of memory. For example, 1 gigabyte. Remember, the operating system must find a contiguous space of available memory, and it may simply not be able to find that much memory in a single block. The default behavior is to throw an instance of an exception, and this is actually going to, by default, terminate the program. We'll see how to deal with exceptions later. However, right now the default is that a program's execution would be terminated and all previously allocated memory would be immediately given back to the operating system. Alternatively, it is possible to force new to simply return a null pointer if the memory is not available. So here, for example, we have new, but it's suffixed with a parameter no throw. Now, the implementation of this in C++ is beyond the scope of this course, but what this will do is it will either return an address if the appropriate memory was found, or if the appropriate amount of memory was not found, it will return a null pointer. At this point, you can then check if the local variable a_data is equal to the null pointer, then you can do something in the case of an allocation failure. Now, in this course, we're not going to deal with that much memory. But when you're working in industry, you cannot assume that any request for memory will automatically be successful. Because if it's not, the consequence is that the program you are running actually terminates, which is probably an undesirable response. So following this lesson, you now know that arrays are allocated using new with a given type name and a specified capacity. They are deallocated using the delete operator that has an empty square brackets after it. You know that dynamically allocated arrays can be initialized like local arrays, or they can be left uninitialized. And you are aware that exceptions are going to be thrown if there is a failure in allocation. However, this can be overloaded so that new simply returns the null pointer if the appropriate memory was not found. Here are the references, the colophon, and a disclaimer. Cheers!